Okay, so once again, welcome to this lecture session, and thank you for joining again. So I don't know how much you are actually getting interest in this topic, but as a continuation, the way we discussed in last 3 days, mainly we covered the regression, but not only in the context of frequencies, as well as in the context of the Bayesian analysis, right? Now, today actually I'll try to cover one specific topic that is basically the clustering and the dimensional detections, which is basically a sort of unsupervised learning. In case of machine learning, if you go to read some specific topic in machine learning, you should know that there are a few topics which is very important, and these topics actually are independent of any data. So it can be applicable to physics data, it can be applicable to biodata, it can be applicable to any kind of data where it's going to analyze data. So I already talk about regression in terms of linear, and also non-linear, sort of in terms of the logistic regression, right? So that actually I try to cover. So I have not yet covered the classification. So classification is a very vast topics, and there are several different kind of algorithms available by which you can actually do a classification in a very clever way. So tomorrow probably we're going to try some classification in terms of random forest or neural network. That we'll try. And today actually we're going to cover the two other topics, that is a clustering, and another is called a dimension reduction. So in clustering and dimension reduction, there are different topics, like the algorithms are available, but since due to this constraint over time, actually I'm going to cover what are the main algorithm people normally use, that is in clustering K-means algorithm, and in dimension reduction PCA, and if I get time I'll talk about TSAD. These are the different algorithm we will talk about today. Now, I just try to give a like broad overview that like when you're talking about data, right? So, like if you remember in the very beginning, in the first day, actually, I was talking about data in terms of some variables, right? Ideally, when you're going to analyze, or when you're going to like design your some mathematical statistical model for your data, you are expecting that your data have lots of variables. So in that case, you're handling a very high dimensional data. So ideally, one data should contain, let's say, hundreds variables. That means it has actually 100 features, and that actually called a feature space. So whenever you're talking about a vector space in terms of data, the dimension of that vector is very high, and it is very difficult to visualize the data itself. And then it is also very difficult to understand what kind of relations those variables has, and we need to actually go through what kind of analysis we can do such that we can understand the visualization and as well as the relation between those variables over that high dimensional space. So so in the context of data science, whenever I have a high dimensional data, first thing we need to do, we need to try to understand what kind of relations those variable has, and is it possible to represent the same data into a lower dimension in terms of 2D, 3D. It actually going to help you to visualize the data as well as to actually work on that part or on that kind of representation. So the representation from higher to lower is very important when you're talking about this machine learning context or data science context. And therefore what we are going to talk about, that is clustering and the dimension reductions. Ideally I should start with very basic of machine learning, but since like I have very limited time, it's very difficult to finish a like machine learning course within a 1 hour. So I'm just trying to give those algorithms which are related to statistics as well as this machine learning topic. So when you're talking about the machine learning, it should have like there are two different type of algorithms available. One is called supervised learning, and one called is unsupervised learning. So in supervised learning, it's like you need to train something. You need to train your model first, and once your model is trained, then actually you want to test. So that is supervised. Like basically, you are helping your model to learn something. So, but in unsupervised learning, you are not actually not doing any test training on your model. Whatever way you want to learn directly from the data, that is unsupervised learning. And clustering and the dimension is actually part of unsupervised learning, whereas regression can be both, but classification actually can be a supervised learning. So today basically we're going to talk about unsupervised learning, and the context is clustering and the dimension reductions. Okay, so I hope it makes sense. Now I just took this picture from sklearn sci-kit. So sci-kit package has several like you can see several algorithms which basically described different kind of this domain. So for classification, what are the algorithms available in sci-kit? For clustering, what are the algorithms available in sci-kit? For regression, even for dimension reductions, all are different algorithms available. And this is a very nice like workflow or like picture which you can, which basically going to help you in the understand that whenever you're going to solve some problem from sci-kit packet or sci-fi packet, how you're going to use those algorithms directly to solve some problem. So you can go and look into those algorithms, and so for those algorithms all the examples are already available, so it is not that difficult to understand for those things. Now, so today I'm going to talk about the principal component analysis. Now so as I said that whenever you have high dimension data, you need to actually try to understand what are the relation between the variables or the feature vectors, such that is it possible to reduce some of the features. So that is actually called dimension reduction. That means, let's say I have a 10 dimensional data vector, and I understood that okay, out of this 10 features, only one or two features are very important and others are not. So that means I need to understand which are the features are very important and how I'm going to represent data based on those features. So we're going to see that how principal component analysis can actually help on that part. So I'm not going to talk about theoretical like mathematics part in details, but like I'll show this code. I'll show mathematically how we can do that principal component analysis too. So let's start with this code. Any questions? Does it make sense, right?
Yes. Yes, sir.
Okay, so what I'll do, so first I'll show some example of a PCA directly using the package from Statistical. Okay, so right now I need some data, right? So I just generate some 2D data here. So you can see this, I just generate some data, and there is number of like 500 data points I have generated, and these are two-dimensional data points, and this data points looks like this. So because I've generated using some Gaussian distribution. Okay, so let's say this is my data, and I want to visualize how my principal components looks like according to this data. I'll come to the theoretical part, what exactly I mean by this principal component. But let's say I have some algorithm called PCA, which I'm going to apply onto this data and to want to see what exactly I'm getting. Okay, so to understand this concept of dimension reductions. So there's a specific function called PCA in this sklearn decomposition class, and you can directly call it. And ideally, since it's n-dimensional data, let's say you have a 10-dimensional data vector, then actually you can decide like how many principal component you want to calculate. If it is a n-dimensional, it should have a number of principal component. So in this case, obviously, is as we are considering two-dimensional vector space, so then the maximum number of principal component will be 2. So that's why it is fixed to 2. Okay, so I just calculate the principal. It is just a calling that specific function PCA with the two component. Once you call this model, then basically you need to fit your data. So that actually I'm fitting here. So once you fit the data, what you're getting, what are the information you're getting? First of all, you're getting some PC component. That's the two that you can see. It has basically it is a 2x2 matrix. That means basically it has two vectors, right? And both of vectors are two-dimensional, right? Now you can understand these vectors are actually at the, like if you remember the concept of basis in vector space, right? Normally we know that if you talk about vector space, there for each vector space there are some basis vectors which actually span the whole vector space, right? So let's say for a simple example, for 2D two-dimensional space, I can say that 1 0 and 0 1 can be a basis vector which actually span the whole two-dimensional vector space in a for real data, right? Like let's say I want to talk about, let's say any point 2 comma 3, that can be written as a linear combination of this 1 0 and 0 1 by taking the this coefficients 2 into 1 0 plus 3 into 0 1, right? So you already aware of that thing, right?
Yes. Yes.
Yeah, so that means ideally we for a vector space representation we can get some set of basis vector which actually able to represent any arbitrary point or any arbitrary vector in that space, right? And that is important because like if you once you know that what are the basis by which you are actually spanning the whole space, you no need to work with individual data points. You can directly represent them in terms of some basis vector, and you can use those bases for your analysis, right? So this basis representation is very, very important concept in the vector space. And when you're talking about this principal component, you can see this principal component actually are two vector in a two-dimensional vector space, right? I'll talk about that what exactly this vector implies, but right now it's just, you can see maybe it is not clear, but if you see this PCA dot component underscore first vector, right? So this is the first vector, right? And this is a two vector, like it has two components. That means it's a vector in a two-dimensional space, right? Similarly, if you just plot this one, then basically it's also a two-dimensional vector, right? So they basically that means that after applying this PC algorithm, what we are getting, we're getting two vector in that two-dimensional vector space. Okay. And now what are the other things we are getting? That is, we're getting some variance and we're getting some mean. Okay, so I'll talk about that later. But now let's say I want to visualize these data points with these vectors. Okay, so you can see these are the data points, and whatever the principal component you are getting, that is basically these two vector, right? Now this visualization is very, very important in the context that now you can understand this data actually showing that how the data is distributed over the space, right? So those and you can see that the variance of the data is maximum along this whatever the longest vector you're getting, right? So this is the first principal component, and it shows that in which direction you have maximum variance of the data. Does it make sense?
But
You can see that the spread. Yeah, go ahead.
like what like for what purpose principal component analysis is used?
Yeah, I'll come to that later. First, try to understand like what exactly you are calculating right now.
Yes.
Okay, so I'll come to that answer to why it is required. But let's say that from this data, it is very clear that distribution of the data is actually you can get maximum variance along this 45-degree angle, right? And that is basically like if I want to understand, okay, what is the one in which direction basically has maximum variance, then the answer is that okay, if you calculate the first principal component and whatever the direction of the first principal component, that will give you the maximum variance.
That 0.95 thing was that, right?
Yes.
Yes.
Okay, so and you can see this in the second direction, the variance is very, very small, right?
Yes, sir.
So in that sense, what we can say that okay, ideally this two-dimensional space actually spanned by these two vectors, this both the vectors. But since the variance in the second component is very, very small, so what we can do, we can throw that vector, and we can say that okay, these data points can be approximated using only the first basis vector or principal component. Does it make sense?
Yes.
Yes.
Yeah, so that means basically we are actually converting, or we are just transforming the data into some sort of approximate version where actually you are removing some of the basis vector.
But sir, like
Okay.
we remove the data associated with that small variances, would it be like not only equal to that uniform distribution only?
Sorry, can you please repeat your question? So
Yes, sir.
some part.
Yes, sir. Like we have removed the small variance data, right?
Yeah.
So then, like, will it be not equivalent to just saying that we are only considering a uniform distribution only?
It is not uniform distribution, right? Like in which sense it is uniform distribution? Like that
Like,
uniform
sir,
distribution part.
we will span the entire set of data points with that big arrow thing, or the data with more variance, right?
Yeah.
So will it not necessarily be uniform?
Right now I don't know that answer, sorry, but uniform distribution of a data means that you are saying that okay, data points are actually uniformly spread, right? But that is not the case here.
Yes, sir. Like I'm not talking about that thing. Like after
Yeah.
we've done that rejection.
Yeah. After removing that variance, it will be
Yes.
in a uniform. Yeah, that is right. Perfect. After the transformation. Yeah.
Okay. Got it.
Okay. Yeah. Okay. So like right now for this example, it may look like why it is required because it is two-dimensional data, right? But when you're talking about very high-dimensional data, I'll show you that let's say it has some 64 dimension or 80 dimension, 100 dimension, right? For that, it is very difficult to visualize the data, right? Because we have a limitation up to three to visualize the data. So for those data, it's very difficult to work. What kind of representation we should choose, right? So for that, it's like since we can remove those direction or we can remove throw those points in rough sense in which directions the variance is less. So in statistics, whatever direction is important is basically there where actually your data variance is maximum, right? Because if you let's say if you remove some data points from maximum variance, like location from my maximum variance, then basically you are actually losing some identity of the data, right? But if you let's say if you throw some points which in direction the variance is less, it might not be like that difficult, like change the actual representation of data. So that concept is very like important in the context of the variance. So the principal components actually help you to understand in which direction data has maximum variance. Okay. Now for the same data, as I said that okay, if I'm going to just uh, consider the first principal component, right? So then I can reduce the dimension, but not the context of like I'm basically reconstructing all the data points, considering only one PCA or only first component. Basically, like you are writing all the points now based on the first basis vector, that rather than writing a linear combination of two vector. Okay, so if I do that, then basically I'm getting a new data set, and the dimension of the data is same, but it is actually the approximate version. So that is written x underscore reduced. So it is the approximate of the data set, and if I plot the approximate version and the original version, then you can see that the data sets are a little bit changed, right? Because after transformation, considering the first principal component, you are only not looking into the variance along that direction rather than other direction, right? So your data sets representation a little bit changed because you just throw away the second principal component. Does it make sense?
So what is this fancy box equals to?
What is
Fancy.
Fancy
That
box.
is for
oh, for that is for the visual, like making that this box
stuff.
for the label. So this legend is basically to this to give to make this box. Sorry, where actually you are just they give the labeling in the original and the projected. So if you just make it is false, or if you don't write this, then basically you will not see the representation of the box in that way. Yeah, does it make sense?
Yes, sir.
It's just a simple plot. So if you don't want, you just make this way. So then you can say that okay, that box where actually you're labeling all those, it will change, right? Fine.
Yes, sir.
Now well, like there is a like once you have transformed the data, right, you need to also know how to like again come back to the original data representation, and for that you need to use the inverse transformation. And if you use the inverse transformation from that class, then basically you can get back the data again. Okay, so this is just a simple representation of PCA using sklearn. Now I'll talk about the maths part. Okay,
Yes, sir.
up to this, is there any questions? No, right?
No, sir.
Okay, so now I'll talk about what is the maths behind that, right? So I already told that there is a two principal component, right? It's basically a 2 cross 2 vectors, right? It is a vector in a two-dimensional space. Now how this came, right? That is the one question which we need to understand. Why it is two-dimension right now? Since obviously for this data we are working with a two-dimension, that means with maximum we can choose the dimension of 2. So it's very obvious, but for the real data or for the high dimension data, it may not be that easy. So what we need to do, we need to actually first understand in the context of variance. As I said, that the principal component provides the direction at which the variance is maximum, right? So that means basically what we're actually looking for, let's say we have a two variables, slope and intercept, like as is given the example last 3 days. So for that, you try to understand what is the relation between the intercept and the slope, right? And that relation only can be calculated if you calculate the covariance matrix, right, in terms of the variance. So covariance matrix structure normally contains all the information of the variance with the variables itself in the diagonal, and the off diagonal actually gives the variance with among each other, right? So if I say, okay, I have some variable x and y, so I can make a covariance matrix which contain the first element should be sigma xx, and sigma yy in the diagonal, and off diagonal should be symmetric in terms of sigma xy and sigma yx, right?
Yes.
Fine.
Okay.
Now, yeah.
Nothing, sir. Like there was this issue. You may continue, sir.
Okay. So now, like, let's say I want to understand the maths behind the PCA. So what I can do, I can from the data I can directly calculate what the covariance matrix, right? So
Yes.
what's the covariance structure for data? So then actually you can calculate this covariance structure for the data from the specific function in NumPy that is called cov. So I use that cov function to calculate the covariance matrix structure, and you can see this is the covariance matrix I'm getting. Okay. So now it's from this covariance matrix, like this covariance matrix structure, you can also, like, if you don't want to use the covariance function from NumPy, you can also write your own simple one line code to get back the covariance matrix. So this is the covariance matrix in terms of mathematics, that okay, covariance matrix basically it's a empirical covariance matrix. The empirical covariance matrix is basically x transpose x. So if you see, this is NumPy dot, I'm just doing that x transpose x between the data, right? So it is giving a covariance matrix. Now there's one catch. So right now you can see these two vector, these two, as I said, that's covariance matrix equivalent to x transpose x, right? So ideally it should match, right?
But sir, like it has to be normalized.
Yes. So actually I like intentionally I have not done yet, because I want to show you that if you not normalize, then it is not exactly match. But if you normalize, then ideally it should be exact, not exactly same in terms of the all the digit, but at least it has up to some decimal it will same, right? So you can see that these are almost same. Makes sense, right?
So,
So
like,
this covariance function is very simple function. Yeah,
sir,
go
can
ahead.
we say that this difference is because of each of x values have different variances?
Yes,
The data itself, because of
yes,
we are getting this difference.
yes. So that's why I said that there is two terms: covariance structure and the empirical covariance structure. So empirical covariance, so the definition which right now I'm using to generate this covariance matrix, one by total number of samples into x transpose x, that is basically the empirical covariance. So you are not actually, you are just because you need to normally covariance matrix, actually if you see, there is a, you need to subtract the mean also, right? So you need to calculate the mean for each case, and you need to subtract that part
X
two.
minus mu upon sigma.
Yeah.
Yes.
Yes. Yeah. But more or less they are similar, right? So you can do that also, and again you can do the same thing with considering there's another function called empirical covariance, and you can calculate that one also, and you can see these are three are almost same, right? Up to some digit. So okay, so so that means right now what I did, we have just calculated the covariance matrix from the data, right? Now once you actually calculate the eigenvalues and eigenvector of that covariance matrix, that will give the direction of the eigenvectors and the eigen, like and the this scaling factor for that data. So you know, if you just see what are the eigenvalues and eigenvector I'm getting, right? So from the covariance matrix, I'm getting eigenvectors. The first eigenvector is this, right?
Yes, sir.
And from the PCA, I'm also getting the same, right? But only is that there is a minus and plus minus difference, right? But that can be possible because like it is just a rotation, right? Either you're taking a vector in this direction or opposite direction, that is the same thing. So sometimes happen that, like, if you directly calculate like empirically, it might be possible that your rotation is not like the way you define the rotation, that might not be same as some calling some function. But if you see the absolute value of these elements are exactly same. Okay.
So can we say that it is simply the transpose?
Actually no, right? Because you can see there is a one difference, right? Here actually it is a minus. Oh, okay. So you're saying it should be
Transpose.
transpose of, yeah, I think so, because then basically it's the first element of this actually come to here, right? And this can be went here, yeah. but like you understand that the point, right? That
Yes.
the elements are same. So that means the way we are directly calculating this PCA from that function, this is similar to the way we are calculating here by first generating the covariance matrix structure and then taking the eigenvector and the eigenvalue.
Yes.
Right now, from this eigenvalue, you can see that the first eigenvalue is very very like if you take the ratio between these two, right? So this ratio is very high, right? Because the first eigenvalue is much higher as compared to the second one, right? So that means we can easily like neglect the second eigenvalue or corresponding eigenvector, and that's why in that same plot you say that the for the second principal component we can just remove it if we want, right? So till now, is it clear that what exactly PCA does?
Yes.
Okay. Now, now I just took the PC component and what I did, I was just taking the, so this is called just a dot product between the data and the PCA. So basically, I have a PCA eigenvector and I have all the data, right? So if I take the dot product, basically it's nothing but the projection of the data onto the PCA component, right? So what I did, I just calculate the projection of the from the data, okay, onto those PCA, and that will actually give you the representation of your new data point, which actually I showed earlier as a reduced data, right? So when it's calling the reduce function from the PCA class, basically it actually taking the projection of your data onto this PCA component. Okay, so if you make a plot for both the cases, you can see that representation are same. So this is coming directly from the function from sklearn, and where actually it is calculated directly taking the projection of the data onto those PCA. Right?
Yes.
Does it make sense?
Yes.
Okay. So I'll go a little bit quickly now. If you just plot this
Sir,
reduced
I have,
version, yeah.
I have two small doubts. One is, can we quantify how much information we lose in projection, or do we lose information at all?
We lose information, right? Because like you can see from this plot, our actual data points are actually in this direction. In the red points are actual data points, the original data points, right?
Yes.
But if we remove one PCA component, now data points actually change, right?
Yes. So,
But you can say that, yeah.
can this loss be quantified?
Yeah, that in terms of the variance, or what I said, right? That like, right now you can see that there's an overlap between this representation, right?
Yes.
So in terms of the data structure, you can say the max, like if you let's say the way I was talking about the ellipse, the error ellipse. So the error ellipse of the original data and this reduced version has some angle, but they have maximum overlap here, right?
Yes.
So you are losing some information in terms of those points are very far away from the core, right? But actually, whenever the nearby data normally it's a maximum clustered in the core, right? So, most
Yes.
of the data points, right? So for that, you can actually you can actually get back whatever the information you want for that.
My second doubt is then a few lines above you wrote a code to reverse the projection. My doubt is whether this inverse projection is unique after we have lost the data.
Yes, that is a good question, but that depends on like either your basis vectors are orthogonal, right?
Yeah.
So if your basis vector not orthogonal, then this inverse is not unique. But we can make orthogonalization considering a Gram-Smith process, right? So
Yeah.
we can, whenever you have eigenvectors, we can make them orthogonal, and then it can be unique, because you know that like let's say I have a two eigenvector which is orthogonal, then basically if I multiply, then one of the eigenvector dot product between two eigenvector becomes zero, right?
Yes.
So the effect of that eigenvector completely nullified, and in that case you can get back the reverse actual space, right? So when you're operating from both sides by some eigenvector, that's the projection I'm saying. You need to multiply in such a way that it can give identity, right?
Yes.
And that identity only possible if you actually it is a normalized orthogonal eigenvector.
Yeah, got it, sir.
Okay. But yeah, that's a good question. Normally, like if it is not orthogonal, then it's very difficult to get back to the actual space. But it is very easy to do an orthogonalization, at least for two dimensional vectors, considering Gram-Smith process.
Yes.
Okay. Now, you can also try to understand that like right now for this example, right? First principal component contains some variance, and second principal component contains some few quantified variance, right? So we can understand how much variance actually it contains in terms of the first and second, right? So let's say I just keep some numbers 0.97. So like I'm considering 97% variance actually contained by the first eigenvector. So if I just choose that, then you can see that this new representation has only one PCA, right? So that means up to 0.97 percent variance actually can be covered or can be defined by the first principal component. So let's say if I just give, let's say 0.99, right? So for to cover the 0.99% variance of the data, you need both the eigenvectors or both the principal components, right? But if you want, let's say, 0.9, then might be you need only one eigenvector, right? That means basically your first eigenvector is actually able to contain 90% of the variance, right? So this quantity actually help you to understand how many principal components required, right? So if you say, okay, for my data, I'm okay with 90% variance, like preserving the 90% variance, right? So then might be one principal component is enough, right? But I said, no, I want 99% preservation of the variance. Then obviously it is required two, right? It makes sense, right? So now if you calculate the ratio between the first two variants, the first two variants of the principal component, and if you just plot them, you can see what is the maximum variance actually contained by your individual principal component. So here actually you can see that it started at 0.975, right? So that means this is that much maximum variance actually covered by your first component, and therefore if I put 99.98 here, then obviously I need two, right? So this ratio actually help us to understand how much covered by the first, how much covered by second, right? And if I take 1 minus of that, that will be the minimum information I'm losing, right? And that is basically 0.025. And I can from using only representing data using first principal component, I am actually able to preserve 97% of the variance of the data, right? Does it make sense?
Yes.
So this is the statistics we're going to use. Like let's say if you said that okay, if you did the principal component analysis, how much variance you have preserved. So the answer is okay. First tell me how much you want, right? Based on that, I can decide how many principal components required. Okay. So so I think how much time I have actually to cover lots of things. Okay, so it's clear, right?
Yes.
Yes.
Okay, so after I'll just little skip here, but obviously I'll go through if I get time. But what I'll do, I'll show, like right now I'm showing the PCA for the two-dimensional data, right? And obviously for two-dimensional, it's very easy to understand that only one is required if you want to do that thing, right? Now the same thing actually I want to show with higher dimensional data points. So right now I'm just taking some data that's basically some digit data from the sci-kit package, and you say these are the different digit data, and this for this data, what data you're getting, basically it is just image, right? So for image, it's a, let's say it is a 8x8 image, so then 8x8 pixel image, then basically for that each pixel you can actually save the image data. Okay, and that data is actually saved here, so we just use that data to see what kind of representation you can do. Now if I check the data shape of the data, you can see this has basically 64 features, right? That means that this data is actually in a 64 dimension space, right? Okay, now for this data, what I do, you just rather than going for the 64, like obviously the maximum of principal component should be 64, right? But we are just only interested in two, so we are going to like calculate only two principal component for that, and we just want to see what kind of representation we're getting. So I'm doing the same thing the way I did in the previous case, right? So we are only generating the two PCA component for this data, and then basically we are representing the data in terms of these two principal component in a two-dimensional space, right? So now from 64-dimensional space, actually it's actually coming to a two-dimensional space. Okay, And this two-dimensional space, these digits are looks like this is the visualization of this digit image in two-dimensional space, right? Now if I want to see that how much variance of the data actually I able to contain by making this two-dimensional representation of data, so then actually you need to what you need to do, you need to actually calculate, right, that what is the cumulative variance you're getting considering different principal component, right? So now you can see if you only choose one principal component, then basically you are actually able to preserve only 20% of your variance, right? That is very less variance of the data.
Yes.
But if you increase your number of principal component, and obviously if you increase, let's say, to 64, then basically you'll able to preserve the full variance, right? And let's say we interested to preserve around 0.95, right? So then basically you need to represent by 35 number of principal component, right? So now from out of 64, actually it is almost reduced by, let's say, half of the eigenvectors, right? Our principal component, right? So that means plus that actually it helps you to reduce the dimension, as well as you can also able to visualize data in the two-dimensional space, right? Does it make sense?
Yes.
Yes, sir.
Okay, so
Sir, one doubt I have. Can
Yeah.
you make a statement that the original data will be covering most of variance? Like the statement is very nice. In at least square root of number of dimensions. Because sir,
that I don't know.
let's
Like how why is square root of the dimension?
sir,
Like
also
let's
that can be seen from this graph also.
so the square root of 64 is actually the 8, right?
8, so it will be around 10, right? So from
So
there, the
around
saturation is starting. Around
so
10.
but around 10 you are actually able to preserve almost 0.8, right? But 80% of your variance, right?
80%. But sir, like from that point, the saturation is starting.
I think this is the point, right, where actually saturation is started, because after that it's almost a
Right,
constant,
sir.
right? So here actually the optimal is 30. So I don't know how to relate with the square root, but normally I know that from this expression or from this cumulative variance calculation, you can get back what should be the number of optimal principal component required for
Like,
you.
sir, I'm making that
data.
statement because like generally we can't remove the signal noise by 1 over root n, right? From there, I'm trying to recollect this. I don't know whether it would be a nice comparison to do or not.
Yeah, probably I'm not aware of that. Sorry. Maybe I'll look into that and I'll let you know. But this is the way normally I know how to tune your number of principal component.
Yes,
Okay.
thank you.
Okay. So I hope this part is clear, right?
Yes,
Okay. Now you can see this from this representation. You are actually like, I don't know how much you already know, but let's say roughly you can say that it looks like there are some sort of cluster of data, right? So some data are actually clustered together, some data are actually part of little bit away from that cluster. So you can say this is a sort of representative of a cluster, right?
yes.
Yes.
So now the second topic which I'm going to cover, that is basically how, let's say I have some data, how I'm going to identify either the data has some specific cluster or not, right? So when actually I'm talking about cluster, basically it's like a sort of group, right? Like let's say for this workshop, someone coming from X college, someone coming from Y college, right? So I can say, okay, this X college basically are one group of students, right? So they can be a part of one same cluster. Similarly, who are coming from Y college, so they can be part of same college, that they are actually part of same class, right? So the grouping of those data is very important to understand how much like how many data actually are correlated, and how many data points are very like anomaly, like these are not a part of any cluster, right? So I can say they are basically independent, or they are not actually directly related to your data, other data points, right? So that clustering actually helps us to understand either data contains some anomaly or not, right? So what I'll do, I'll show you some cluster representation here. So what we're going to use some k-mean clustering algorithm. So k-mean clustering algorithm basically says that, okay, let's say I have some data. So you need to fix how many actually cluster you want. So let's say I want 10 cluster, right? Or so 5 cluster. So then k-mean cluster actually provide, finally, it will provide you a 5 cluster of the data representation. Okay, so first I'll show you what exactly we're doing, and then probably you can talk about that, right? So right now, what I did, I just generate some simulated data, and this is very good data set. If you want, you can go and check this data, this make underscore blobs. What it will do, it will help you to generate some like how whatever number of clusters you want. So here should I fix number of sample equal to 500, number of features 2. Basically, I'm talking about clustering in the two-dimensional space, and then the number of center equal to 10, right? So that means I am generating a data set which has basically 10 clusters. Okay, so it is just I am just for verification that okay I am generating those data set, and now you can also fix the standard deviation for each cluster, and if you vary like this, let's say I choose 0.1, right? Let's say if I choose standard deviation 0.1, then what should I expect? Whatever the clusters I'm getting in that clusters, data points are very nearby, and therefore you can see the visualization should be that you can directly see those clusters, right?
Yes.
Right, but if I choose, let's say, a little bit higher standard deviation, that means data points are spread around in that cluster itself, then basically you'll not able to see that very clear cluster structure, right?
Yes.
So now this is the way you can like if you choose very high standard deviation, then basically you can see that it is very difficult to see the cluster representation data, right? Though it has 10 cluster already, because the way we are designing or we generating data, it has actually 10 cluster, but it is not clear because all the data points are now overlapped, right? Now this is our input data, and we want to apply the k-mean clustering over there, and I want to see either k-mean clustering able to give a proper like cluster representation or not, right? Okay, does make sense? Fine,
Yes.
right?
Sir, a doubt.
Yeah.
Have you chosen the sample centers randomly?
This random state which is given, right? So you can fix the random state, and based on that you can get a same center every time. So if you change this random state to some other, then obviously it will change the center. So to answer to your question, it's yes, I'm changing the center point randomly, but right now it is fixed to 0. So every time when you're going to generate it, it will always generate the same 10 cluster with same center.
Okay.
Okay, but ideally if you change that random set, then obviously you'll get a like at one trial you are getting one set of 10 central center, but if you're in the next trial, if you change the random set, then basically you'll get another set of center. Okay. Okay, so I was going to use the k-mean clustering from the sklearn, and I just to visualize, you can see that right now we are getting some. So one problem with the k-mean clustering that you need to provide how many cluster you want, right? So ideally from data, if the data is unknown, how you know that how many cluster is important, right? So you need to basically need to do the in the trial way. And let's say right now I'm just giving 8 cluster, right? So then one you are providing k equal to 8. So basically you can make k equal to 8 here. So let's say I'm making k equal to 4 first, right? So then basically this k-mean cluster actually provides you a 4 cluster, right? So according to the k-mean clustering, this cyan color and this yellow color are two nearby cluster, right? Ideally they are nearby cluster also in the data, but in between this data itself there is a small cluster which is not able to recognize because you are considering 4 cluster here, right? Now if you increase the number of cluster, then those big cluster can also be divided into small cluster, right? You can see, right? So does it make sense?
Yes, sir.
So applying this algorithm, it will provide some number of clusters, but that will be user defined, right? So then it is a problem, right? Because how you know that how many clusters actually is the optimal number of cluster? Okay, so then basically there's a specific statistics code which which you normally going to calculate. That is called basically Seal-Houghton score, and if that Seal-Houghton score actually going to help you to understand how many clusters actually optimal for your data. So for now, for this case, if I calculate this still how they score, we are getting around 0.41, right? So ideally, if you're getting around if you're going towards 1, then basically it provides, it says that okay, whatever the number of clusters you're getting, that is the optimal one. And if you're going towards, let's say, 0, then basically it will say that okay, the clustering is not good and it is a worst clustering, right? So this score actually going to help you to understand how you're going to analyze your how you're going to optimize, or how to identify optimized number of cluster for your case, right? So now if you make this cluster score 10, right? So then you get basically a little bit higher value, right? But itself it's not that good, right? Now I need to understand for different cases how this score can vary, right? So I'll just show you the visualization right now.
There are doubt.
Yeah, sure.
For a given data set, its silhouette score be a bimodal distribution? As in, can different number of clusters have the same optimal score?
Can you please repeat the question? Same.
I mean, if it turns out that the actual data has something like 10 centers, but something like 5 or 6 centers have the same kind of optimal matching, can this sort of a situation arise that the possible distributions of the silhouette score itself is bimodal or something like that?
Like if there are two such type of centers which have same value.
No, actually, it's like you are bimodal in the sense that if you fix the threshold on the Silhouette score, let's say 0.5, right? So let's say for this example, actually I fix the value at 0.5, the threshold. So ideally, what I should, if I make, let's say for this example, if the number of clusters is actually 10, right, and all the clusters actually very easily like distinguishable. So then basically all your average Silhouette for each cluster should cross that threshold, right? So for some cluster, if it is not crossed, right, then you can say okay, like if you make a bimodal at 0.5, right, then you see some peak around greater than 0.5 and some peak less 0.5, right? In that sense, it is a bimodal.
Yes, my question was more like, can a data arise where the 8 centers and the, let's say, 3 centers both reach somewhere near 1? In that
Yeah,
case,
that can be possible. Yeah.
In that case, how do you decide whether the data has 2 centers or 8 centers?
Then no, you are not going to looking into the actual solution. Like you are only going to looking into that whatever the representation you are doing using k-mean clustering, that does it actually providing a good representation or not.
Okay.
It might be possible that it is not exactly matching with your number of cluster, original number of cluster, right?
Yes.
But still, how the score actually going to help you to understand that representation actually is you can use that one or not for
Yes.
further analysis. Okay, so it's like that, like for one same questions, answers can be different, right? So the host who is going to check that question, there's no specific answer for that, let's say, right? So it's like that. But the student A and B both are actually coming up with two different solutions. So if the answer of that representation is correct, then both of them getting a good answer, a good number. So it's just like that kind of thing. So Silhouette score only help you to understand that whatever the number of cluster actually you have done based on this k-mean clustering, either it makes sense or not.
Okay. Yes.
Okay.
Yes.
So for this example, you can say that if you make, like say, 9 cluster or 8 cluster, right? For that also, all of this average Silhouette score for all the cluster greater than 0.5, right? So you can choose this one also as a good solution, or you can choose this one also as a good solution, right? But it's up to you, right?
Yes.
So now if you see, like for some example, let's say for this example, but this is not the good answer, right? Because here you make 2 cluster and one of the cluster has very little bit high, like just some of the value actually cross that part, so it is not a good solution. But whereas if you think about this is also good solution, this is also good solution. right? Or it can be also the grid solution. So it's depending on like what kind of representation you're getting, and based on that you need to decide either you're going to choose that one or not. So there is no such a ground truth which you're going to recover from this approach.
Yes.
Okay. So so now the question is, let's say here actually obviously it is very difficult to understand the cluster representation because all the cluster actually mixed up, right? But let's say I just change this variance to 0.5. Now you can see the Silhouette score is very, very high, right?
Yes.
And why? Because here actually data itself actually has some sort of cluster representation. So for k-mean clustering, it's not difficult to actually recognize or to identify those clusters, right? So that means whenever you have a very high standard deviation in your data, or very like completely mixed up data, then basically it is very difficult to identify what is the optimal number of cluster, right? Fine.
Yes, sir.
So yeah, okay. So I think I have. I just want to. I just want to finish one more topic. Can you just please give me a like 5 to 8 minutes, not more than that. Okay.
Yes, sir.
Now the question is, right now actually I talk about this dimension reductions and the represents of data in the two-dimensional space or lower dimensional space considering dimension reductions, and also cluster also giving some kind of representation, right? So now the question is, if I want to understand like both the methods together, which one is like the dimension reduction versus this clustering approach, then what kind of like for the same data, what kind of information you're getting, right? So what I did here, that okay, for the same data, this digit data, I already did the PCA, right? And now for the same data also, I can do a clustering. Okay. So now if we do the clustering, you can identify basically what are the levels for individual digit right now, because this is a digit, right? So for individual digits has some specific level. So some data, if it is actually, if some image basically is 9, so it's basically is part of class 9, right? So if it is 3, then it is part of class 3. So it's basically these are the different 10 different classes right now, let's say. And for that actually you can, and you know what are the hidden like specific representation you're getting from PCA, and what is the representation you're getting from the k-mean clustering. Okay. So from PC and from the k-mean clustering, you can actually get the same representation, like this 2D representation. But only problem is that in k-mean clustering, you don't know what, like how to how you're going to like in PC you don't know how to actually get back this label, right? So right now what I did, I just yeah, so you can see here, this is this is a specific label which is directly so maybe I should, so since I have a little less time, so I'm not going to probably you can go and check the specific level of this data. So as I said that since it has some specific level, right, 0, 1, 2, depending on like what is the location of the image, right? So if it is, let's say it's 9, so the level of this image is 9, right? If it is 3, then level is 3, right? So this is the origin level for each data, and this is the levels actually which we are actually generating, or we are actually obtaining after the k-mean clustering. Okay, so we did the k-mean clustering of the data, and from the data locations, from the clusters, we actually calculating what should be the labels of those clusters, because for each data points you know what are the data points, and for each data you can actually calculate what is the label, right? So here actually I will just only calculate the label of each individual data point from those cluster, and then we just try to color them together. Okay, does it make sense?
Yes.
Yeah, okay. So you can see for this data, obviously, we are using the label directly from the given data set, and this is from the cluster, right? And you can see more or less they look similar, right? That means the PCA representation and this cluster representation provides similar kind of structure, right? Yeah, so like that means for this data set, you can also use k-mean clustering if you want to do a cluster analysis, Or if you want to do some further analysis in terms of data representation, then you can also apply PCA. Okay. Now this also implies that, like, for some high dimension data, if you're not able to work with, let's say, 1,000 dimension data space, then you can just use PCA first to go to get back into the 2-dimensional space or 3-dimensional space, and then you can do a cluster over there, right? So that means the PC and cluster can be operate together on a data set.
So, sir, this clustering of data sets is also used to make high resolution images for the faraway planets.
Yeah.
Right.
Yeah.
Like sir,
Yeah.
this type of PCA and like my friend has told, they are used for hyperspectral analysis, the PCA
Yeah.
methods and those things, because
Yes,
the
yes.
data is very vast and also number of beds are also very high and data is
Yes.
contagious too.
Yes, in astrophysics, this dimension is a very important topic, because normally whatever the data representation we have, they're more or less similar, right? They have some anomaly, but they have more or less similar. So you no need to work with high dimension data. You need to actually use some lower dimension representation of the data, and that for that this is a useful topic to explore. Okay, so right now actually I was talking about the PCA for in terms of this covariance matrix structure, right? But there's just a one. I'll just take a 2 minutes. Sorry, I'm on. It will not take more than 2 minutes. So there's another topic, specific dimension reduction technique that is called. Sorry. Okay, so there's specific method is called this TSNE. It is also dimension reduction technique similar to PCA, but it is non-linear in the sense that rather than actually it is just calculating the covariance matrix structure in the high dimension space, it is actually calculating basically the probability distribution of the data. So like if you want, if you read the actual paper or the Wikipedia, so I just want to show you what exactly I want to say. Like if you have high dimension data, basically you can choose some distribution of the data in the high dimension space, right now you can say this is basically exponential, that means the Gaussian one, right? But for that Gaussian distribution, you can actually define, you can provide some specific distance definition. Okay, so when you're going to calculate that, okay, this data set has basically a Gaussian representation in high dimensional space, you will basically first need to define how you're going to calculate the distance between two nearby points, right? So two vector. So here actually xi exit to a nearby points, and you first need to calculate what is the distance between these two in that high dimensional space, right? So you can choose Euclidean distance or you can choose some other distance. So normally when they design this algorithm first, they choose Euclidean distance, but normally high dimension data, at least for some signal space, it is sort of non-Euclidean space, and there it might be possible that the Euclidean distance definition may not be valid. So in that case, you need to use some other definition of distance, and you can use that one to represent your Gaussian distribution over that space, right? And then basically what you're doing, you're calculating the ratio between two different points by taking this Gaussian distribution representation, and from there actually you are going to compare your approach. So this is sorry, where I was. Okay, so for the same data, you can also apply this TCNE that basically based on some distribution rather than directly defining in terms of the Gaussian Euclidean distance. Does it make sense? So for PC or for this K-mean clustering, we are assuming that we are in a real space and the distance can be defined directly using Euclidean. Whereas when you're talking about this approach, it actually calculating the distance in the high dimensional space considering some distribution, and that distance can be a non-Euclidean also. Okay, and if you apply this algorithm, then also you can get some set of cluster representation the way you get from the K-mean clustering or PCA. Okay, does it make sense?
Yes.
Okay, so yeah, so I'll share this iPython notebook. So I think I'm not sure either you're going to apply those algorithms or these algorithms in the latest stage or not. But it is better to learn all those things, because in the real scenario or real problem, these are the very useful algorithm to explore. Okay, that's it. Any questions? No, right? So I can stop here.